Hello, my name is Katherine Jinkins and I'm currently a postdoc in John Rogers' lab at Northwestern University. However, today I'll be presenting my PhD work in Mike Arnold's lab at UW-Madison on exploiting liquid crystal assembly at a liquid-liquid interface to uniformly align carbon nanotubes in a scalable process. Individual carbon nanotubes exhibit some of the best semiconducting charge transport properties ever measured. For example, nanotubes have exhibited conductances nearing that of ballistic transport, and additionally, their ultra-thin body electrostatics enable excellent gating even with the aggressive downscaling of device architectures. These results are extremely exciting. However, transistors and electronic devices must be based on arrays of highly parallel nanotubes at intermediate packing densities, as unaligned nanotubes reduce drive current and crossing nanotubes increase device off-state variability. If the charge transport properties of single nanotubes can be exhibited in aligned nanotube arrays, nanotubes promise to lead to faster, more power-efficient semiconductor electronics for applications including computers and logic, radio frequency devices, and thin-film transistors, as well as enable flexible electronics. This development of methods for the alignment of carbon nanotubes on the wafer scale has the potential to improve the performance and energy efficiency of semiconductor electronics drastically. My work focuses on the development of such nanotube alignment methods. One technique for aligning carbon nanotubes that has been promising is floating evaporative self-assembly, or FESA. This technique was developed before I started my PhD in a collaboration between Professor Padma Gopalan and my advisor, Professor Mike Arnold. They empirically discovered that by dropping nanotube ink, or nanotubes in an organic solvent, at a substrate suspended in a water subphase, films of alternating stripes of aligned and random nanotubes could be deposited. Field effect transistors fabricated on FESA-aligned nanotube stripes have demonstrated current densities outperforming silicon and gallium arsenide. These results are very exciting, but the FESA process is not ideal for multiple reasons. Ink droplets are very difficult to control and scale, and the random regions cannot be used in high-performance electronics. At the beginning of my PhD, my goal was to uncover the actual mechanism in FESA in order to overcome these film shortcomings. I determined that the aligned stripes deposit from nanotubes that collect and confine at the ink-water interface, and we hypothesized these nanotubes were aligned by large outward flow or shear. In this current work, we wanted to study the assembly of nanotubes at the ink-water interface and the effect of flow independently, and use this to develop a new technique for nanotube alignment. To study the assembly of carbon nanotubes at ink-water interfaces and the effect of flow independently, we construct a new experimental setup. Here, we create a channel comprised of two substrates. Half the channel is placed in water, and we use strong directed fluid flow of the nanotube ink to align nanotubes from the ink-water interface across target substrates. Using this channel, as opposed to one substrate as in FESA, reduces the amount of ink we need and allows us to reach higher shear rates easier. This process would look something like this. Initially, the substrate channel is suspended in water. Nanotube ink is added and flowed through the channel. The nanotubes almost immediately collect at the interface, and the flow serves to align the nanotubes. By translating the substrates through the flowing ink-water interface, uniform films of aligned nanotubes are obtained. We call this process and technique tangential flow interfacial self-assembly, or TFISA. In practice, the setup looks like this. These are the two substrates, and this is the needle which disperses the nanotube ink. We found that by angling the channel like shown, we are able to achieve a more uniform deposition across the substrate. This video demonstrates the TFISA process. The deposition occurs very quickly, so the ink will flow between the substrates, and then the substrates will be translated through the flowing ink-water interface. Additionally, we found that the nanotubes are aligned across the upper substrate with the steeper angle with the water, while the lower side of the channel has thick mats of primarily unaligned nanotubes. Using this setup, we can isolate the effect of flow on alignment. Here are SEM images from TFISA films obtained without flow, where the substrate is just lifted through a stationary ink-water interface, and with flow. We can see that without flow, the nanotubes are still densely packed and highly ordered with respect to each other, and the nanotubes align with the addition of flow to be oriented within a tight half-width at half maximum of plus or minus 5.7 degrees. However, even with zero flow, continuous films of local domains of aligned nanotubes are formed. This is the first indication of the underlying role of liquid crystal phenomena on the alignment technique, which I'll discuss in more detail later in my presentation. Comparing these Defects films to FESA, we see that the Defects technique eliminates the striped nature of FESA while retaining the high degree of nanotube alignment seen locally. We also use two-dimensional fast Fourier transform analysis to quantify the variation in the local nanotube alignment angle or the local director as a function of flow rate. With outflow, the local directors are oriented at all angles, showing a lack of global ordering. With intermediate flow, the local directors begin to align with the majority direction, and at high flow, the global alignment approaches the high degree of local nanotube alignment. This improvement in alignment and film uniformity can also be seen in these polarized optical microscopy images, where a brighter yellow indicates the nanotubes are aligned with the flow direction, or the horizontal, and the regions that are darker are where the nanotubes are changing alignment direction, or the density is decreasing. We can see that the POM images become much more uniform and the nanotubes more directionally aligned at high flow. However, even in this high flow rate sample, there are small imperfections within the film, as indicated by these darker domains. We found that these areas actually correspond to liquid crystal defects within our nanotube films, confirming the formation of liquid crystal assembly at the ink-water interface. I used the understanding of the underlying role of liquid crystal phenomena to guide our further experiments. For example, increasing ink concentration also serves to improve the overall alignment and order within the Defects films, characteristic of lyotropic liquid crystals. Here, we observe liquid crystal defects at concentrations as low as 5 microgram per mil, much lower than concentrations needed for bulk liquid crystal assembly, indicating the importance of the two-dimensional ink-water interface to achieve this liquid crystal assembly. Additionally, at a concentration of 100 microgram per mil, intermediate packing densities of 50 nanotubes per micron are achieved, which is near optimal for nanotube field effect transistors. In liquid crystals, reducing temperature increases the importance of anisotropic van der Waals interactions between messages and serves to improve order in liquid crystal assemblies. Here we see that at 35 degrees Celsius, there are a lot of these darker defected regions in the nanotube films. However, these defected regions are almost eliminated completely at 10 degrees Celsius. SEM also shows highly aligned nanotubes free from liquid crystal defects. Field effect transistor measurements demonstrate that Defects arrays have excellent electrical characteristics with substantially reduced variation compared to FESA films. Here, I fabricated transistors using E-beam lithography across FESA and Defects films and used SEM to correlate their performance with the film morphology. First, as we travel across the FESA film, we can see the effect of the random areas is to reduce the on current, leading to large device-to-device variation in performance. While in the Defects film, the on current is much more uniform, due to the highly aligned nanotube arrays uniformly deposited across the substrate. This is just a small subsection of the devices measured. Here, all the devices are included, so you can see the lower variation in the Defects transistors due to the elimination of the random stripes in FESA. Additionally, an excellent subthreshold swing of 60 millivolts per decade is demonstrated from Defects arrays by using an ion gel top gate for increased electrostatic gating. To prove the inherent scalability of this technique, we uniformly align carbon nanotubes across a 10 centimeter wafer piece. Shown here is a photo of the actual substrate with Raman spectroscopy maps of nanotube density overlaid. As seen between positions 2 and 3, where the flow is well formed and steady, uniform films of highly aligned nanotubes are obtained, evidenced by the uniform color and SEM. To confirm the role of the ink-water interface on the Defects technique, we applied large amounts of shear to bulk nanotube ink without the water present. We see that without the ink-water interface, the nanotubes are only quasi-aligned, with more crossings and misalignment, while the Defects films have very different film morphology, demonstrating the importance of the two-dimensional ink-water interface to achieve liquid crystal assembly and a high degree of nanotube alignment. Finally, I'd like to acknowledge the other authors on this work, including the Arnold Group members, Dr. Robert Jacob Berger and Dr. Vivek Saraswat, as well as Sean Foridori. I'd also like to thank my collaborators, Professor Padma Gopalan, Jonathan Dwyer, and Professor Argentile Bearson, as well as my PhD advisor, Professor Mike Arnold. Thank you.